Hello and welcome to the Sound on Sound People and Music Industry podcast channel. I'm Sam Inglis, Editor-in-Chief of Sound on Sound magazine, and I'm very pleased to be joined today by Igor Levin, the founder of Antelope Audio. Welcome, Igor.
Thank you for inviting me.
You're welcome. I think the name Antelope Audio will be familiar to the vast majority of our listeners here, but your own story is perhaps a bit less well known. So I wonder if we could kick off by asking you to share a little bit about your background and your history.
Basically, I was born in the Soviet Union, and when I was 14 years old, I emigrated to the United States, where I then went to the university. I was accepted at the University of Michigan in Ann Arbor, Michigan, where there I studied electrical engineering and computer science. So I have a sort of a dual degree in electrical engineering and computer science, and this was in the early days. Nowadays, maybe it would mean a lot. It's actually quite complicated, and things have been divided into so many other types of engineers. But there I was, and when I was growing up as a young person in the Soviet Union, I had interest for electronics, and I started building radios. And these were the days when you had to design a lot of things that using discrete components. This was in the Soviet Russia at that time. Integrated circuits were very few and difficult to find. So anything you wanted to build, and I wanted to build radios and tape machines and audio amplifiers. So you had to do it with like a discrete components, transistors, even some vacuum tubes in some instances, although I haven't done that much with the vacuum tubes. But this was very interesting because with that background, it prepared me, now in retrospect, looking at all the modeling that we've been doing, that many things we model are designed with discrete components, with transistors, resistors, so on and so forth. And so that's sort of, for me, it's a very fun trip in the memory lane, going back to my times of my childhood when I was soldering these things together on a wooden board. And so it's really lovely to even look at the devices and see how they're constructed, because even the way the old printed circuit boards are made, or they weren't really printed circuits, some of them were just discrete point-to-point wiring. But so that's where the background, my childhood and my interests. And then, of course, at the university, I learned lots of math, lots of physics, lots of signal processing. It's actually quite a tough university. And that sort of opened me up for the digital era. That's when things sort of moved from analog circuits that I was very fond of. And I was still as a consultant right after the university. A lot of people were hiring me to do some analog circuits for biomedical, for lasers, for whatever, because analog engineers are still very much in high demand. But by that time, I already started programming in C, C++, and later down the line, signal processing algorithms, and so on and so forth. And so that's how. And there in that town, I started another company that was called Aardvark. And in the early days of audio, and I've built a lot of things, again, starting out with clocks. And I think Antelope and also Aardvark are pretty much known for their clocking devices and the clocking innovation that early on I had a few inventions that proved to be quite fundamental and important in terms of achieving certain sound, which we're still using in our devices. The acoustically focused clocking technology that we talk about. And that goes to those early days of Aardvark. And then down the line, moved on from clocks. We made some SPDIF stuff and some interfaces. And then actually we started building multi-channel interfaces. And in fact, we had some interesting, industry firsts. Like, for example, we actually shipped the first 8-channel line level in and out interface in the world. I think predating just by maybe 1 or 2 weeks another company that was working in the same domain. And then later down the line, I built the world's first audio interface with a microphone with a digitally controlled mic preamplifier built into it. And in fact, this was around, I think, year 2000 approximately. And that also had some DSP processing in it as well. It had a signal DSP processor At that time, it was a Motorola 56301, I think it was called, family 24-bit microprocessor running at about, I think, 80 or 90 megahertz clock rate, which is about, 1/6, 1/7 of the DSP processors in our current products. Quite interesting. And we were still able to do quite a bit with this one processor, where we had the EQs and compressors on the channels, and we had a little reverb going. And so, but putting the mic pre into it was one of the biggest innovations, I think, as well as maybe putting everything together like that. And in fact, at the trade show at the time, people were quite shocked. They couldn't understand what was the box with like this mic pre's. With these jacks, because they were not used to that. The audio interface was like a line in and line out. And when they saw this box, and the typical conversation would go like this with the microphone jacks, they would go, okay, what is this? Is it the mixer? And we say, no, but it has a mixer. What is it, a mic pre? And, no, it's not a mic pre. It's yeah, so it's not a mic pre. Why does it have this in the mic jacks? Well, it's an interface. Well, no, it can't be an interface, because interface has to have line-in jacks. And so it took a while for people to kind of integrate, move up to this thought, which of course now is pretty normal. Almost everybody offers interfaces now with the direct connectivity with the microphone. But it was quite innovative, and this was about 21 years ago, if you think about it. So then, as things developed and over time, then Aardvark stopped existing, and my next company was Antelope Audio. And in Antelope, it was the same thing that I was working on, but now being extended on a higher level as the technology progressed, and there's more components now. And so we have one of the early innovations that the fundamental to Antelope was a 32-channel interface working on a USB. And this is really something that sort of launched us into the interface world. And even that was quite a shocker at the time, because people USB overall had a sort of a bad rep at the time. People were avoiding, they were using FireWire or whatever they could, but not USB. And so just to have something working on the USB, and to have something working on 32 channels at 192 kilohertz in and out, people were just like quite shocked or not quite convinced. So it took a little bit of time for them to actually say, wow, this is really working, and it's working on Windows, and and it's working on Mac. So that was good. But to make this thing work, we had to develop FPGA solutions. This is how and why, because I think maybe you may want to talk about FPGAs, or I don't know, that may be an interesting topic because it's so unique to our company. But we turned to FPGAs in order to maintain reliable multi-channel signal flow through USB. That's how we accomplished this 32 in and out. And that required a unique design using this programmable devices, field gate arrays, that we actually accomplished. So that's maybe a little bit of a background and where things stand.
Thank you very much, Igor. And yes, absolutely. I think we'd all love to know more about the FPGA solutions that you've come up with over the years. For those that aren't aware, FPGA stands for Field-Programmable Gate Array, and it's a somewhat different technology from both native processing, where audio is processed by the CPU in our computers, and from DSP processing, where the audio is processed using dedicated hardware chips. And FPGA is something a little bit different from both. I wonder if you could explain what those differences are.
Well, FPGA, is just basically a chip that's sort of by itself, it does absolutely nothing. It has the building blocks. It's a chip that consists of hundreds of thousands of basic digital circuit building blocks that you can write an algorithm, you can write an instruction how to wire the chip individually, how to wire all these things together so that they can be useful in some ways. So once these things, and you write that using like typically Verilog or VHDL, that's a special language that is created to instruct the chip how to make these connections. But essentially, you're not executing a program. a DSP or computer, it's running a program step by step. Step one, take this number. Step two, add it with this number. Step three, put it into this memory location, and so on. Whereas an FPGA doesn't work like that. It has a clock, and on each clock beat, the signal flows through all these hundreds of thousands of mathematical or building blocks performing something for you. And so that's sort of essential difference in that a DSP processor works sequentially, executing things one step at a time, whereas an FPGA is hundreds of thousands of things working in parallel, wired together, kind of like your brain, where all these things are connected. And so that's sort of the difference of a circuit. Much the same way, say, if you have an electronic circuit, like in your compressor, like all these transistors, resistors, blah, 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 they don't work sequentially. The electrical signal just flows through all of them at the same time, and out comes the result. And so this parallelism is the main difference, which one of the main advantages is a hugely larger signal processing power. Because when you have hundreds of thousands of things that can work together, that's sort of a little bit different than versus having like one DSP chip that can do things one step at a time.
Thank you, Igor. That's a very clear explanation. And in a lot of Antelope products, you've used this AFX technology to provide processors that appear to the user like conventional plugins. Is it quite a big step to get from this FPGA processing to a conventional user interface that people understand?
Well, yeah. I mean, many of these things are just the problems, and these are sometimes daunting problems, because the problems of user interfaces and the problems of presenting a paradigm to a person in an intuitive way oftentimes is much harder than purely mathematical or electrical or engineering problem, because you're dealing with human beings, and which have different so you're again dealing with psychology and person's backgrounds and their learning. It's interesting how even software from different countries, like I think the DAWs that are made in Germany have a distinct different way how UI is presented versus, say, North American DAWs. Because I think there's something about the cultural element even of people who design these things, aside from their aesthetics, like whether they prefer darker backgrounds or lighter, or icons like this, just sort of like the British styling or the European styling. There is this thing. And so the presentation element, it's not to be underestimated. That's what makes or breaks sometimes a company or product. So yeah, that's not a simple thing.
You've used the FPGA technology to create emulations of classic studio hardware like compressors and equalizers. That's something we've seen other manufacturers do using conventional DSP hardware. Do you have to take a different approach to do that in your FPGA-based technology?
Yeah, it's completely different. I mean, this is like, it's the difference between parallel processing versus sequential processing. And just the way, parallel processing, or even, there's computer languages and algorithms that are presented in doing things simultaneously. But for people, they're much harder to comprehend. It's just that the way our brain works. And so when you're creating an FPGA, you're not actually programming it like an algorithm. You're not telling it, do this, then do this, then do this. You're telling it, okay, connect this with this. So you're creating a topology of the chip. You're not telling it how to do it, in which order. You are actually connecting it. You're connecting the building blocks. So it's a little bit maybe more similar. I don't know, there's audio software products where you have these icons and you kind of drag them together and you put, two wires to the third icon, and it represents a mixer or maybe an oscillator. So like if you're doing this stuff that's synthesizers, they're sometimes programmed with icons. So like this type of programming is closer to an FPGA programming, where you are actually creating a structure These are structural languages. They define topology. They're not sequential languages. Computer languages are divided into like declarative and versus procedural. So declarative, they declare relationships or something, and procedural is the ones most people are familiar with, like do this, then do this, then do this. And so that's like two different worlds, as well as trying to do things where multiple things happen in parallel, like 2, 3, 4, 5. Like imagine it's like watching 5 movies at the same time with a different plot and trying to. So it's much harder. So FPGA is really the only people who can design these things are really chip designers that have had experience with these things. So naturally, it's a lot more daunting. Incidentally, maybe this is a good time to mention that we are not the first company that got this idea or popularized this idea or stepped on this idea. RME, in my view, is arguably the first company that really took the approach of using FPGA chips. And in fact, they did so in order to do their, I think they have a mixer. I don't remember what they call it. It has an interesting name, but it's the one that can do lots and lots of channels. And then you can put on like an EQ and a compressor and of the same kind in each channel. So that's what impressed me is, RME are the pioneers and they deserve a special fund mentioning on my part. And that's really what inspired me. I mean, I took the idea of using FPGA from them, and then I developed it, whereas in their world, like if they have a compressor EQ, it's always the same compressor, same EQ, whereas I was able to generalize this idea where you can have many types of compressors or many types of EQs. And that's sort of, but in terms of programming, yeah, I mean, programming FPGAs is a nightmare and a half, and very few people can do that. And whereas, programming DSPs is something, that's done in C or C++, and that's generally like a second-year student or, something that by the time you finish college, you should be comfortable programming in C and C++. Certainly a lot more accessible and popular, and there is a large database or there's a large amount of already existing algorithms on GitHub or other places that you can practically take and use for signal processing on a DSP chip.
That sounds as though it must pose quite a challenge from the recruitment perspective to find people who have the skills you need.
Well, that's the approach. Then we took a different approach. Instead of we tried to make these things more general purpose. And so once we designed the processors on the FPGA, we designed general purpose processors on the FPGA so that then programming them becomes a task similar to programming a DSP chip. And so, but designing the processor itself is not trivial, but, we've had over 10 years to work on this thing and several people worked on it, myself included. So there's a lot of work that has gone into that, but mainly, and also because of the factor that you mentioned and the flexibility that's involved, yes, we definitely at a certain point in time considered augmenting the system of FPGAs with the general purpose DSP processors.
That, as I understand it, is what you've done with the latest generation of processing at the heart of your newest interfaces, which you're calling the Synergy core. Is that right?
Yeah, that's exactly right. That's the idea, to basically have the best of, have your cake and eat it too, or, both worlds are best, but that's the thing, because at that point we've done a lot with the FPGA and we got huge performance and a number of vintage effects, but there are weird effects. There's weird and interesting stuff that doesn't really easily reduce itself to a standard paradigm, and that requires more of a general purpose processor such as a DSP processor. And that's plus and ultimately, we've done a lot of work on our own. We've developed lots and lots of effects. I think, maybe 50 effects, which is quite a bit. But then there is also a whole community of other people that have been working in DSP. And so at that point, we kind of thought, okay, we want to open up the ecosystem and we want to bring in the new partners into the game. And that's why we need to have sort of a procedure or system that people are familiar with. So we need a standard DSP processing thing being a part of our ecosystem, and then we can open the system up and we can have partners and we can run all these pre-made algorithms that other people developed, and there's no way in hell we'll be able to use, such as autotune, for example. Like autotune would not be practical to put on an FPGA chip.
If we look at the range of AFX processors that's currently available, there's a huge number of vintage compressor and EQ emulations, not quite so many reverbs or delay-based effects. Is this to do with a limitation of the technology, or is there some other reason?
There is some of it just has to do with the flow of how we got into the business of developing these things. And that we firstly made a universal processor on the FPGA that was specialized in doing EQs, and then we made one that was specialized in doing compressors. And so then we made one that was a reverb, and we made things that are like preamps and guitar cabinets and so on and so forth. So some of it is the order in which we were developing these things. And so then ultimately, when it came to time-based effects, we sort of ignored them a little bit. But they're currently we have 7 or 8, I think, that are offered right now when you take into account the various flangers and pedals and there's I know that there are a few more in development and in various stages of QA. So by the end of the year, we're going to see quite a few more of those. And now with the DSP, there is a certain types that we can do that we couldn't just do before, and so we have more freedom, and we should be able to do more of them. But I think with some of the stuff is also the question is trying to figure out what we should be doing next, because we already have quite a huge library of these things. And I think that what's great is we try to do this process somehow by listening to our community and what people are asking. So I think what would really help us and focus us, people to tell us, okay, what do you want us to make next? And we have a huge community, so that's also interesting. So because maybe guitar players will have one idea and maybe mastering engineers will have another idea or whatever. But ultimately, yes, I think we are going to do a lot more of them. And what would be great is to just get people involved. Like, what's your view? What kind of effects do you think we should make? How would you decide if you had to decide?
Well, there's already a huge range of effects available for AFX. I mean, I haven't explored half of the ones that exist already, so it seems greedy to demand more. But one thing that is characteristic of the AFX and some other systems too is that a lot of the processors are designed to be used on the input side, so you would actually record through them and print the processed signal. For instance, if you have a mic preamp emulation, or in your case, actual modeling microphones. Do the AFX actually have the ability to change the characteristics of the analog circuitry on the preamp side, as in some rival products, or is this all handled entirely in software?
Well, a couple things on that question. They're not specifically designed to be used on the input side, because you can, by means of using the routing matrix, actually direct them and use them as inserts in your applications. Arguably, this is not the most elegant way to do so. A more elegant signal flow would be, or a workflow would be, to just open them up as plugins and have all that magic happen under the hood. And that's something that we do with our AFX DAW technology that automatically wires these effects in while presenting them as VST and plugins, and with all the automation attendant and working. Yeah, so these things are certainly and absolutely not hardwired into any particular application. In fact, that's sort of cool about our router in general, that it's very, very flexible, especially with the high-end products. You get our drag and drop router where you can really build the amazing signal processing chains. But I think that initially, or a lot of people were using them with the signal coming in. But you don't need to do so, and certainly we expect with AFX to do a lot of people using them rather conventionally by just installing the plugins, and that's why we developed the AFX to DAW. On the second part of your question, does this change input impedance? I think that was what you were referring to. Our philosophy, or my philosophy, and our philosophy is that we want to take the signal, bring it through the amplification with the least amount of distortions or change, and have it converted as clean as possible. And any other kind of modification that reflects the presence of some circuits would be done actually as a DSP. So we do not actually alter to be consistent with that technology, with that thinking. We do not bring in elements that would alter the signal, because, say if you want to do controllable impedance, where do you draw the line? How many different kinds of impedances would you allow? 1, 200 ohm, 500 ohm, 2 kilo ohm, 1 mega ohm, what if you had a device that was none of those? Then does mean you wouldn't be able to model it, right? So, and what do you do with the people that bought your devices before, and now you have this plugin, but you don't have that circuit, so they wouldn't be able to use that plugin. So in order to stay clean and consistent with the idea of just bringing it in as pure as possible and then doing all the processing through the DSP, so that's how we do it. We basically model the effects that a particular impedance would have.
Well, that makes good sense. Another thing I wanted to ask you about plans for the future is we've seen other manufacturers who make DSP-assisted plug-in boxes make their technology available in other formats. For instance, you could buy a satellite unit that simply handles co-processing and doesn't have any I/O, or we've seen companies use their technology in guitar foot pedals, for example. Do you have any plans to do that with the AFX?
Well, the technology is there. We certainly have the IP. So on a purely technical level, that would be a relatively straightforward thing to use it into various applications such as these. And it's great that you're mentioning that, because we're definitely open to suggestions and comments by both power users, media hosts, and community in general. Everybody looks for ideas, but let's take these two questions separately. The question about accelerator box. My general feeling is that we make a range of devices taking into account, starting with the $499 and then going to multiple thousands of euros. Okay, so they have a somewhat different budgets and different expectations. The guy that's really at the lower end of the scale, he's really very, very budget conscious. A box like that with the attending costs of various plugins for it is something that's probably out of his range at that point. And then the guys on the very top, they really need some serious signal processing. So one advantages we have in this whole process, because we're using FPGAs, and everything we have has FPGAs, and so that by accelerating it with both FPGAs and DSP chips, we generally offer several times the amount of processing that's available in other similar devices. So that leaves a lot extra DSP power in the devices themselves to be used for the AFX to DAW applications. And more expensive, higher level devices actually have more acceleration. So for example, with the Rhine Studio, which is a very, very nice upper mid-level device, you're already getting 2 FPGA chips and 6 DSP chips. So that's quite a bit of processing power. And if you bought Galaxy, you would have gotten 12 DSP chips and 3 FPGAs involved in the acceleration. So the way we build them is just basically thinking that it's somewhat matched to the needs of particular customers. So at this point in time, we think that the boxes themselves providing enough access capability where, an external device is not necessary. But if we hear the customers saying, we love this stuff and we really want even more acceleration, then, we'll listen to them, and, you may expect something like that. Or maybe there's another application that I'm missing, trying to figure out like how that would fit in. But at this point in time, I think what we got now is a good starting point, certainly. In terms of your second question, I think that refers to pedals. That's an interesting one. And I think there is more of a question, okay, how would the Antelope pedal be any different from any other pedals, And that's sort of, we're not fond of just making something just to put an Antelope logo on it, because, ultimately people aren't that stupid, and they will not, if the product is not compelling, they're just not going to buy it. And so we need to really understand, again, and we're a pretty open company. We're open to the community, and this is something really customers really need to do for us, and we need to hear from more people like that. If they say, okay, we like this effect, or we like the way this thing sounds, or it could be used like that, then we would feel that there is a compelling reason to actually build a pedal, and we would do so.
That makes perfect sense. If I could ask you another future-focused question. Antelope Audio were early adopters of the Thunderbolt protocol, and you've also made a number of USB interfaces. In fact, many of your interfaces offer both connection protocols. Do you see much of a future in studios for Ethernet audio?
Well, we actually have gotten into it. If you think with the Galaxy products, where we have the Ethernet connection, that's already available. But I think that's a different thing. It's really, I see Ethernet thing as more like a larger institutional audio type of projects. I think the biggest users of such things are like educational institutions that like to have different rooms connected, or extremely large studios maybe, or some live applications. Currently we have Dante connectivity. But at the same time, the world is scaling down. And, that's something that we've also seen during the COVID times, during the lockdowns. We've seen a lot of people staying at home. And sort of interestingly for the industry, it was a boom in sales in terms of like these small devices, because all these people staying at home wanted to like get back to their hobbies and so on. So like this small thing, I don't see how that would fit in the Ethernet. So maybe wireless, if anything, if one day there was some sort of a wireless thing. But currently with cost benefits analysis, I think that some of our new devices like ZenGo, which are powered from the laptops, and that's something it's much more practical, I think, at this point in time, as well as provides better quality and much lower latency as well. I guess I'm not that gang-ho on the Ethernet audio, although it certainly does have its place in the live applications.
Okay. So talking about the AFX to DAW plugin, if you're not familiar with this, it's a plugin that allows you to use the hardware-based AFX processors within your DAW software as if they were native plugins. That's been available for a while on Antelope interfaces running on Thunderbolt on macOS. Any news on when that might be extended to Windows or to USB?
I'm glad you asked. Actually, I have good news, and I love delivering good news. In a very short time, we are actually going to make all the stuff that's currently running on Thunderbolt Mac. AFX to DAW will be available on Windows Thunderbolt. So that's available. In addition, we have finally made a bold step into supporting this technology on the USB. So beginning with the ZenGo device, we will be able to also offer AFX to DAW on the USB, and that's on both Mac and Windows USB.
Oh, that's fantastic news. I'm sure you've made a lot of customers very happy there.
And it made me happy because it's just so difficult to, it took a lot of efforts to get this thing working, but I'm really happy how it worked out.
So, what's your general approach when you're creating a model of a vintage processor? What's your starting point, and how do you refine it till you know it's right?
Well, that's an interesting thing because that's sort of a combination of art and science, at least as I see it. So the way I like to work, and there's different people have different ways of working at it. But I like to work with the schematics because to me, schematics, it's sort of like a building plan of the circuit. And so by just looking at the schematics, you get sort of an idea of the uh, I don't know why a quote from Einstein comes where he said, "I want to know God's thoughts, and the rest are just details." I think he said something similar to that. And I want to know the thoughts of the designers of these things. Because some of these people are extremely brilliant and they have signatures. So when you look at how the schematic is made, you can sort of feel there's certain personality that to me comes across. And so that's why I like to see the schematics. And the schematics also often gives away what he's trying to accomplish. But there's interesting because some of these things, you also see the imperfections. These days, we're very spoiled. We're very lucky. We have like various CAD software and modeling software. So you have something like Spice or LT Spice, and this is the software that allows you to really model, build these circuits without physically building them and send all kinds of signals through them and audio and see, you can really record the result. And it's really, really amazing. And watch these voltages and currents. But what you find out in that is also that there is, when it comes to vintage devices, there is a number of uncertainties and a cool sort of contradictions. For example, one thing is that as they issue the same device over, say, 4 or 5 years, they may actually go through 3 or 4 or 5 internal revisions without, the public thinks it's just one device, but then certain resistors or capacitor values may be changed from version to version. And there you may be facing an interesting choice as a person modeling it. Which version do you want to model? Do you want to model the early version, the middle version, the last version, or maybe model several of them and allow them to switch between them? And then the other thing is you find out is that some of these people, because they didn't have all the stuff we're having now, they made mistakes and they didn't realize they made them. I've seen the devices where things are not quite working perfectly, or there's mistakes in the component values and even mistakes in how things are connected. I have also seen some products where in manufacturing process, they didn't notice that one of the wires or connections on the board was actually missing. And they got into manufacturing without realizing it. And so then the question is, okay, is that a feature or a side effect? Because sometimes it could be a lucky thing when, something is missing, but maybe it sounds special because of that. And so do you fix it and then model it, or do you leave it like this? There's so many imperfections, like a classical ones, the settings on the decals that say like it's at 5 kilohertz or 2 kilohertz on the EQs generally do not match to the real ones. And then the question is, okay, do you fix it or do you leave it? Because with digital modeling, you can make 3 kilohertz to be exactly 3 kilohertz. Or should you make it 2.6 as it is? And, so those are the interesting choices. That to me is fascinating. And then comes the question of aging of components, which is, fairly explored in the microphones. When you model the microphones, membranes are physical things, subject to moisture and handling pressure. And when you model a given microphone, which one do you take? And those membranes, they're sort of retightened by hand. And so all these things, there's a huge ambiguity which goes with all this vintage stuff. And that's where the art of it comes in. The other element, okay, once you understand the circuit, you need to figure out what model and what not to model, because you can't model everything. If you try to model every component literally, you're likely, you're going to bring the computer to a halt. And so you need to really figure out what's the quintessential, what makes the circuit or what makes that device, and what it is that you want to emphasize and some stuff that you want to de-emphasize or maybe let go. So those are the fascinating stuff to me. And then comes the question of choosing the actual algorithm, because the algorithms or the digital methodology is not perfect either. And they have certain methods do worse on lower sample rates, certain methods do worse on higher sample rates. And then what precision do you need? And that's where, with the FPGA, we have that benefit that when we design these processors on the FPGA, we actually select the bit width, that we process a particular signal flow, and we adjust it as needed for that particular application or in that particular case. Unlike, let's say, a DSP processor that's made to work with a 32-bit floating point or whatever, we can actually work with wider bit width, and we do so with certain, with EQs, for example. To have an EQ sound good at the lower frequency cutoffs, you need a lot more bits. And so sometimes we go to like 64 bits or 70 something bits. These extra bits, they really do help, especially at higher sample rates. And so these are the things, the flexibility that we have, but that has to do with the analysis and then understanding of these limitations. So we're talking about the analog limitations, the aging factors, the imperfections in the transistors, and the limitations of the algorithms. So only after you can sort of have a handle on this whole, on all these number of issues, that's sort of the fascinating choices as a designer you make. And that's sort of, that's what excites me. And that's what excites me in the vintage stuff, because it's just really not black and white. It's really, not like the pictures of the period.
So, what's been the most difficult item to model?
Interesting. It's just the ones where you don't know. Like, did he mean it like this or did he mean it like that? Now, in terms of, these days I'm on the German wave. And that's, I find the German, some of the German compressors, they're just fascinating. Like this, and the approaches they have, like this one, like when he's got this release circuit, he's got this thing, in addition to the usual timing, he added a counter that counted 2.5 cycles of the wave before he engaged the release. And this is like happening in the background, and they figured out for lower frequencies that makes it smoother. Like what's unusual are these like sort of interesting thing. Like right now I'm working on a device called Dynaset U311, which is I'm sort of doing as a hobby while I'm on vacation, but this is fun for me. And that one is like has 2 separate thresholds. It's like a compressor with 2 thresholds. And for each threshold, it has like its own ratio. So you can have like this really weird looking compression curve, like where the bottom threshold could be either compressor or expander, and the top one can be compressor, expander, or anything in between. So the unusual stuff like that, that's sort of what fascinates me. But I recall like some of the EMT compressors that was like a nightmare to model, just too many diodes. And when you get stuff with too many diodes, the equations become nonlinear, and it's sort of difficult to solve them in real time. But on the other hand, there was something where we got some kind of a version where some of the wires were missing on the PCB, because I think it was one of the last things they produced before like the company went under. And so I was trying to figure out what the designer actually meant to do. And he must have been under a lot of pressure at that point, or I don't know, what was going on. So it's interesting. I guess they're all great. And it's sort of like your children. And just because it's a difficult child, it's not, at the end, everything is lovely in their own ways.
Well, it's fantastic that we have now these devices available for all of us to use, courtesy of your emulations.
Yeah, and hopefully, I'm hoping that other people can enjoy them in a different way, because I'm not a musician. That's although I do sing, but certainly don't produce music. So I'm hoping, I enjoy these things from like sort of a dorky, quirky engineering point of view. And so now I'm also hoping that I want to have guys try out this like double threshold compressor thing on drums and really see how they can get some really unique sound out of that.
Yeah, well, I look forward to hearing how they do. Thank you. As well as modeling classic studio hardware such as compressors and equalizers, Antelope have also launched quite a comprehensive range of modeling microphones. What are the special challenges involved in modeling how a microphone works?
That's a very interesting one. And the main one, it's sort of along the lines of vintage, because I think some of these microphones are the most vintage things that we model, with the original designs going back into quite a bit into the past. And so one of the challenges is finding the right specimen, because, these microphones are now strewn over different studios, and each person thinks his microphone sounds the best, right? So, but these two things, they're just sort of like vintage wine. So if you go Burgundy, say 1957, and then got 10 bottles from the same place, and so you're going to find like there's some inconsistency. So finding the right microphone that you think that microphone is the one we want to model, I think that's sort of more than half of the battle. Then the next question is measurements and algorithms that you use. One of the unique things about our modeling algorithms that we do this as 3D modeling that models the sound, off axis, on axis, and off axis. These are for when you use our modeling microphones that have two capsules, because you need to have at least two capsules to be able to do like this 3D thing. And so that generally it does the best job modeling microphones that are constructed similarly. There's a number of German microphones that have like that very similar construction with the two capsules. And so those microphones are modeled fairly accurately. Now, when you try to extend it out to different kind of mics or maybe dynamic mics, and so it's sort of like, well, it's not the same thing, but it's similar. And the algorithms, they will optimize something, and you don't have enough degrees of freedom to optimize for everything. So then you need to tweak it, and you need to do a lot of listening tests and to try to figure out which one really comes closer to it. I think that those are the biggest tricks that are involved. And then essentially, yeah. So in general, that's sort of like the modeling. Modeling is a little bit like drawing pictures, but imagine sketching someone's face. There's artists who with just like one or two sketches or with just two lines, and you immediately look at that and say, yeah, that is this person. And you can have people who just draw and draw and draw at the eyes and the ears and everything. And at the end, you're not so sure. So that's sort of the ability to focus in on the essential that I think is what makes good models versus not so good models.
That's a lovely analogy. I like that.
Yeah, and in general, I think that's sort of, and sometimes the other thing you find out in audio and in video and in generally in the world of art is that realism is not real. And that's sort of an interesting thing. So that sometimes when you make it when it's mathematically exactly right, it may not be exactly right in terms of the sound. In the early days of television or in the photography, they found out that if a photographic image reproduces exactly the amount of contrast that's out there in the scene, then such an image will look to you pale compared to the original, because there are some psychological factors such as size of the image, amount of lighting, that affect how you perceive contrast and color. And so generally color reproduction is a bit fake. It's sort of, it exaggerates certain, you need a certain amount of stylization and exaggeration. in order to make it sound right. Just like being in the theater, like the actors in the theater or in the opera, their gestures and mimics are so much larger than life. But if you're sitting far away, it just seems to be just about right. So in modeling, like when people were doing tube amplifiers, people have certain expectations how tube amplifiers have to sound warm. Well, it turns out that if you actually model the tube amplifiers exactly how they are, you will not find out that they sound like tube amplifiers. So that what a lot of people do is actually they over exaggerate the tubiness or the tube distortions just a touch, or sometimes not a touch, sometimes 2, 3, 10 times, and then it just about sounds right. So taking psychoacoustics into the factor is a big thing as well.
Thank you, Igor. This has been absolutely fascinating, and I'm sure I'm not the only person who's been hugely impressed with what you've achieved with Antelope Audio over the years. So, if I could leave you with one final question, where do you see the audio interface market going in the next 5, 10 years? What's the future for audio interfaces?
I always thought that the stuff I was doing was 5 or 10 years ahead of its times. So if you want to see what it will be 5 or 10 years from now, then look at the stuff I'm doing now. And it's a little bit funny because the work I did is in Aardvark days, right? In the year 2000, I've introduced an 8-channel interface that had the digitally controllable mic pre's and had the processing on each channel and the reverb. I think it took about 10 to 20 years for other people to have products that are similar. So in some sense, that's sort of what gives me an idea that some of the stuff we're doing today will become commonplace maybe 10 years from now. So, and in terms of going further, that's a little bit difficult to do. In general, there seems to be a trend towards virtualization. So the interesting thing is whether there will not be an opposite trend, because some of the it's interesting thing is in the nature or in the philosophy or in the nature of people, things sort of move in sort of a pendulum way. And in terms of fashions, you see like short hair followed by long hair followed by short hair, or tight clothing followed by loose clothing. So there's these cycles. So the interesting thing to me is, will the virtualization continue? So because I myself have been involved in much of the efforts to virtualize, and maybe another interesting comment to make about this thing, because currently some of my focus is in preserving the history. I am actually sort of an interesting, I realized I'm sort of an archaeologist or something of the sorts, because I'm currently doing a lot of modeling of vintage German stuff. I'm very, very fond of these designs that are very little known in the Anglo, in the English-speaking world. But there's been a huge amount of activity in audio in Germany following the World War II, and some of the most brilliant designs made. And I go back to these compressors, to these EQs or whatever weird things they had, the pre's and the microphones, and I tried to figure out how they were working, understanding how these people were thinking, and to try to reconstruct it in a digital way, so to preserve this forever. Because some of the stuff I'm doing now, you can't buy it anymore. It's not made, and there's very few of them left in the world. So in that sense, I'm now in this sort of archaeological effort where I'm going into the past instead of in the future, because trying to see if there's some stuff in the past that we have missed, and that would be very, very cool to make it available to the young people today and not so young people today, to really enjoy this stuff. But in terms of the future, so I think it's, if I'm thinking about this sort of oscillations, I kind of see that people may at some point become tired of the virtualization. And so sort of go back to, okay, well, how many of us can actually play the piano, or how many of us, so instead of having all these plugins, I can foresee that it may become extremely interesting to actually start building again these things, box after box, with the huge knobs and the dials and whatever you can find of the vacuum tubes, or maybe even there could be factories that will start making vacuum tubes again, just to sort of swing back into this naturalness of things as they were. So and then it's possible to have a synthesis. So maybe we'll have some analog devices that are somehow integrated with the VST world. So that's sort of what I see as some possibilities.
Thank you, Igor. And I'm sure we all look forward to the new range of Antelope audio boxes with enormous Bakelite dials on them. In the meantime, you've been listening to the Sound on Sound People and Music Industry podcast with me, Sam Inglis, and Igor from Antelope Audio. Thanks for listening. And be sure to check out the show notes page for this episode, where you'll find further information along with web links and details of all the other episodes. And just before you go, let me point you to the soundonsound.com/podcast website page, where you can explore what's playing on our other channels.